Okay, so to pick up with Unit 1-5 notes here, you've got these on the example page, so these are there for you. Do take a little bit of time to read through them. I'm just going to summarize a couple things. So, one, we're going to assume that it passes smoothly without leaving the track. The significance there is we should always have continuous graphs. We shouldn't ever see any jumps as we make these graphs. Position, velocity, and acceleration graphs should be stacked vertically. So we'll see a couple examples of what that means in just a minute. But in other words, if I have a position versus time graph and then a velocity versus time graph, I do want the times to line up on those graphs. So if this is 1 second here, I want that to be 1 second as well, so that essentially I could line up those moments vertically and then see what's going on during the segments together. The graphs won't have any numbers because we're not going to see any specific values for most of these, but they should tell us steeper slopes or higher speeds. They should give us the appropriate relationship. So again, we'll see that as we get going. And then finally, this is maybe the biggest one. The position is the position measured along the track. It's not the position from a given point. So what that means, if I have a track that is something like this and then something like this, rather than just defining this as 0 and this as some point where we'd have to find the hypotenuse, the position is just how long it is along that track. So maybe 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. It's not worried about the direction change. And that is a little bit different than what we're used to for position graphs. Right? Normally we would say we'd have to find the hypotenuse between those locations. But we're not worried about that for these particular types of graphs. So anyway, let's do an example or two. So this example asks us to draw a position, velocity, and acceleration graph for the ball on the frictionless track scene. And you could choose to start with either of those three. I actually would recommend either starting with the velocity or the acceleration, and I think you guys will see why. But anyway, they give us this situation. They tell us the initial velocity is greater than 0. So what that tells us is we know it has some velocity, right? Well, if there's no, right, if it's frictionless track, if there's no friction, we know that that velocity is going to be constant for that first segment of the track. But then what's the velocity going to do as we go down the ramp? Well, we know we have an acceleration, a constant acceleration down the ramp, so that velocity should steadily increase, steadily increase, steadily increase, and then down here, right, once it hits the horizontal ramp again, it's not going to accelerate, but it should continue to coast at that new constant velocity. Okay, so again, my advice would be start with either the velocity or the acceleration graph. I'm actually going to go ahead and start with the velocity graph because I think it's a nice middleman. I think it helps us to segue pretty nicely between the position and the acceleration graphs. So I'm going to make my velocity graph first. However, I scrolled down because I am going to put my position graph above it, and then I'm going to put my acceleration graph beneath it. Okay, so I've got my graphs going here. I am going to try and do like those bullets told me to. I do want to try and make sure I'm lining everything up appropriately. So I'm going to try and make sure these all match up here in just a second as well. And we'll scroll down and just take care of the velocity, or excuse me, the acceleration graph in just a moment. But let's start with the velocity versus time graph. So again, I know for the first period of time, and I don't know how long that is, but I'll just call that maybe T1. Right, so I'm marking T1 here, so I should mark it about the same location up here. So again, a dotted line kind of running up and down between them would have them lined up. But I know for the first period of motion, right, it was moving at some velocity that was greater than 0, and it was moving at a constant velocity. So it should just end up looking something more or less like that, right, for the first period of motion. Then we've got the second time, which I'm actually going to make a little bit shorter segment, assuming that all the tracks are about the same length. I'm going to make that a little bit shorter time interval because I know that it will begin to be moving quicker as it rolls down the ramp. Okay, so this is one of the biggest keys with the velocity, is the fact that we know it's accelerating, so we know it's picking up speed. The question is it going to be a curved line or a straight line? Right? So is it going to have a curve to it one way or another, or is it going to be a straight line? Well, the key there is the fact that what does the acceleration tell us on a velocity versus time graph? And the acceleration tells me the slope. And I know that for this particular situation, if I'm going down a ramp without any friction, the acceleration is constant. So that tells me my slope is constant, and therefore it should be a straight line, or a relatively straight line here, going between whatever our initial velocity and our final velocity are. right? So again, there doesn't have to be necessarily any specifics in terms of how high or how low these velocities are, but I do know that whatever my initial velocity is would be down here. My final velocity after it goes down the ramp should be higher than that, and it should be a straight line connecting the two. Then from that point on, I've got T3, which is where it would leave the track, and I'm again going to make that a shorter time because it's moving at an average higher velocity. So if I'm assuming those tracks are about the same length, it should do so a little bit more quickly. Okay, so let's consider then our position burst time graph. Okay, so I'm just marking those times so I've got them to work with up here as well. And the position burst time graph, I'm actually going to make sure I have plenty of room up here to work with, and I'm going to try to make this fairly subtle. But anyway, on a position burst time graph, we know that the slope is the velocity. So if it has a constant velocity, it should have a constant slope. So I'm going to define its starting point here as 0, and then I'm going to make it a pretty shallow slope just so I have plenty of room to work with on my graph, and you guys will see why soon enough. Okay, but it should be a straight line from 0 to there because I have a constant velocity. But then from 1 to 2 seconds, I don't have a constant velocity, right? I have a constant acceleration, which means my velocity is increasing. And if my velocity is increasing, then on a position versus time graph, my slope should be increasing. Now the one thing you need to be careful about here is we should not plot a graph that looks like this, right? I should not plot a curve that looks like that because that would suggest that my velocity down here was 0 meters per second, and it wasn't. My velocity entering that ramp, entering the incline there, should have been whatever it originally was. So rather than starting at kind of the vertex of the parabola, I need to just start the curve with where I left off. So here I'm going to curve it, but it's going to start from that location that I left off at. So it's going to curve something more or less like that. So again, I'm kind of continuously flowing with that slope, but then my slope increases over time. Okay, so that's what that stage should look like. And then the third stage really would continue that curve as well in a straight line though, because once I reach that final velocity at the bottom, I know that it's constant again. So this is where I said I wanted plenty of room, and I still didn't have plenty of room, but this is basically going to go off now tangent to that curve until we get to T3. So we're going to have a very steep incline. Okay, and again, the steepness is important. The graph doesn't have to look exactly like this, but our first leg of the motion should be less steep than my final because my velocity and therefore my slope is higher over here. Okay, so the position is usually the one that has the most going on when you're making it from these tracks. The velocity hopefully isn't too bad, and then the acceleration graph, hopefully you guys all agree, but this one should be very, very easy for us, right? If I'm making an acceleration versus time graph for this particular motion, I know for the first t1 seconds, however long that was, when I was moving down the ramp, I wasn't accelerating, or when I was moving on that horizontal ramp, I wasn't accelerating. So that part of the graph would look something more or less like that. T2 was the only period where I did have some positive acceleration, and again, this would be just the sine component of gravity, but I did have some acceleration here, but it would be a constant, so it would be a horizontal line, and it is okay to have a little bit of a jump there. And then from T2 back to T3, it's going to look something more or less like that. Okay, so my acceleration graph is going to be much more broken here, but that's going to be the graph that we're looking at for acceleration. Okay, so spend some time and thought. Make sure you're comfortable with all three of these. Again, if you have any questions, let me know. You could choose to start with the acceleration graph, and that would maybe help you then work all the way back up. I kind of like the velocity just as a middleman, but do whatever you're the most comfortable with. But hopefully these all make sense for you. So then this example has us go the other direction here, right? This one says use the following sets of data to predict what the ball's track would actually look like. And there is actually a pretty big trick in this one. If we look at the acceleration, we can see that it's 0, which means that it should be a flat ramp to start off with. Then we have a negative acceleration, so the acceleration is working against the velocity of the ball. And that's an indicator that, right, the ball is going to be rolling up a ramp and then back down a ramp. Okay, and we can see that on the other graphs as well, right? My velocity was a positive, 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 but then it starts decreasing. It pauses for a moment at 0, which would be at the top of an incline. Then it starts picking up speed the other direction. The reason I said this one is tricky is because look at how fast it actually ends up going. This one's kind of tricky because it actually ends up going faster than its initial velocity, which means it rolls up a ramp, it rolls back down, but then somehow it actually rolls down further to pick up a higher velocity. So I'm going to sketch this picture out and then obviously elaborate on it a little bit more, but make sure you feel pretty comfortable with what's going on. So without any doubt, I hope the first stage of this track should be pretty obvious, right? It's moving with some initial velocity, so whatever its initial velocity is, we know that that is greater than 0 because it's reflected here and it's reflected here with a positive slope. So the ball is rolling with some initial velocity on a horizontal track. Then it hits that first time, right? It hits that period where it's definitely got to be going up a ramp. And the reason I know it's got to be going up a ramp is because it begins to slow down, right? It's got a negative acceleration and it slows down until it reaches 0. So the ball rolls up the ramp, rolls up the ramp, rolls up the ramp, and then it reaches 0. The tricky part is if that ball just rolled right back down the ramp and onto this, we'd see some symmetry. And what I mean by that is rather than seeing it reach a higher speed and then constant, we'd see it reach about the same speed. So we'd see it reach right about here and then level off. But that's not what happens. So what that suggests is that somehow this track, when the ball rolls up it, maybe it goes kind of into the page a little bit, or maybe the track just changes on its way back, but the ball rolls up and then actually rolls down a longer distance. So it actually rolls down then a little bit further down here to this point and then levels off on the track. Okay, so the ball rolls up the ramp. Again, maybe it goes into the page and kind of curves around backwards and then rolls down a steeper ramp. Like I said, this is a rather tricky example to interpret. I do want you to be comfortable with how I identified that though, right? How did I know it had to have gone down further? Well, that's because the velocity was great, or the magnitude of the velocity was greater than it originally was. So tricky. I don't know necessarily that we would see something like this on an AP test, but you definitely need to be comfortable setting up diagrams like this for the AP test. So again, whether it would actually go down to a lower distance, I'm not sure if that would happen, but you do need to be pretty comfortable representing position, velocity, and acceleration graphs all in the same frame of reference. So a very good skill for us to make sure we're developing. So then a quick conceptual check for us here, right? So what would the acceleration of this look like? Well, the ball's got an initial velocity, it's rolling up, it would reach 0 at some point up here, and then it would return back with the same magnitude, but with a negative direction. So keep in mind this is asking us for the acceleration graph. The easiest distractor right here is A, because you look at A and if you're thinking velocity versus time, this makes sense. If you were thinking velocity, we start at a positive velocity, we go down to 0, and then we reach a negative velocity. That makes a lot of sense. But that doesn't work for my acceleration graph. The only one that makes any sense for my acceleration graph is D, right? It's got a constant negative acceleration. Why is the acceleration constant? Well, it's because I'm going up a ramp and they're assuming there's no friction. So I know my acceleration is constantly just the sine component of gravity, and it's working against me in the negative direction. You could make an argument for C if we knew that going up the ramp was negative. Then going down the ramp we could define as a positive acceleration. But based on standard measurements, D is the best representation. E tries to trick you a little bit too by saying that that moment where it pauses it wouldn't have any acceleration. But if it didn't have any acceleration at the top, that ball would roll up to the top and just stop there, which obviously does not happen. So anyway, hopefully this was a pretty quick concept check for you, but watch out for A. That's probably the most common distraction. So then to wrap up the second part, and we'll finish the last few examples then in part 3, how do we find the average acceleration? And again, I know I've talked about this a little bit, but the average acceleration boils down to the definition of the acceleration. I need to find the change in velocity over time. So if I ever ask you to find the average acceleration, you need to find the velocity at your final time minus the velocity at your initial time, and then divide that by your change in time. So I actually do not need the acceleration function to find my average acceleration. However, if I ask you to find the instantaneous acceleration, that's when you need to find your acceleration function. So that's when we would need to find my derivative of the velocity function or my second derivative of the position function. So instantaneous, we actually find the acceleration function. For the average, you do not find the acceleration function. You just use the velocity function to do so. And we'll see an example of this again in a few minutes.